Welcome to today's panel discussion on heterogeneous materials and considerations for advanced packaging design and assembly. As advancements in electronics push the boundaries of innovation, we're increasingly relying on packaging solutions that integrate a variety of heterogeneous materials. This brings some opportunities for enhanced performance, but also produces significant design reliability and manufacturing challenges. Our esteemed panelists today will explore the questions that lie at the heart of advanced packaging. So our panel today, of course, is heterogeneous materials, considerations for advanced packaging design and assembly. Our panelists today are Chuck Bauer from TechLead Corporation on the end, Ravi Parsathari from Zestron Corporation in the middle, and Grace O'Malley from INEMI. So thank you very much, lady and gentlemen, for joining us. And let's get straight in to the panel. Our first question today is how do differing thermal expansion coefficients of heterogeneous materials impact the reliability and longevity of advanced packaging designs? Let's start off with you on the end there, Chuck.
All right. Well, thank you for having me here, Trevor.
Mm-hmm.
The challenge, I think, with the CTE or coefficient of thermal expansion mismatch is that there are two aspects, and most people don't realize that the real issue is not stress, but strain.
Yes.
And whatever the stress is the result of the strain, not the other way around. And so it's a combination of how much differential is there,
mm-hmm.
and then what is the rigidity of the material stack-up that you're using.
Right.
So if you're using a very rigid material that has a lot of strength, you're going to end up with very high stresses, and you're going to be much more sensitive to any defects, any mechanical defects in anywhere in the stack of it. Even if it's in one of the relatively minor materials, you can get a crack that initiates there because of stress that's imposed on it from the next layer, for example. So I think that the thing that's going to be the challenge is not really going to be the selection of the materials, but rather our ability to model the stack up so that we can actually see where the high stress points are that result from the strain that is occurring between the various layers.
The strain is on the different materials and how they
Correct.
stack up.
The strain is created by a differential in how much the material expands.
Yes.
Fortunately, in most of the advanced packaging applications that we're using in heterogeneous integration, fortunately the dimensions are not huge at the moment.
Mm-hmm.
And because the dimensions are smaller, the actual stresses created by the strain will be more manageable initially.
Right.
But just as an example, very simple example, glass is a very strong material, very rigid,
yep.
and also very fragile.
Right.
So if you have materials that are putting a lot create a significant strain differential between the glass and the next layer, that will be a challenge.
Yes.
I don't see the strain between the various other layers as being as nearly as significant of an issue to deal with as at the glass
as the
interface.
glass. Yes.
So
yes.
It is going to depend on the variety of materials, but it's also going to depend on how well that is managed. And I think we have the tools today to be able to model that much better, and that will help us succeed.
Okay.
Yeah, if I could add to that, certainly it's the age-old problem, isn't it? So we've learned a lot, certainly over the last number of decades, as miniaturization drove us in this direction.
Yep.
And we've started to understand the material sets being much more complex over time and only increasing in complexity now. But as you said, it's requiring much thinner and more sophisticated material usage. And thus the metrology requirements is a big challenge right now. So how do we measure these accurately for the dimensions that are going to be required in heterogeneous integration? So I think it's a big opportunity. We can only model well things we have well characterized in terms of the materials and the expected failure modes. So, that's why there's so much research work going on, at an academic level and in the industry at the moment in exactly those areas, because once we have the information, I think then the tools will naturally improve, organically improve and evolve. And incorporate all the different elements and additional capabilities that we want to leverage in heterogeneous integration. But it comes back to the basics. We need to understand the dimensions and the materials and characterize them correctly and introduce them into the modeling.
Well, I mean, we're just getting used to silicon carbide, and glass is the new one coming down the pipe. So it brings in all sorts of challenges.
Exactly.
What about for you, Ravi, for leading these different things?
Well,
the challenges are you
the
finding?
challenges that you see in heterogeneous integration is the different material subset that's been coming into integrating everything into a single package. So the semiconductor materials, you have the silicon carbide, gallium nitride, indium phosphide. There are so many different novel materials that's coming into, and they all have different properties. Then you are looking at the substrates. There is a different set of substrates, like you have organic silicon interposers. So all these materials bring in their own challenges. So when you're trying to stack all these materials into a single substrate, like Chuck mentioned, you have the strain, and all those things are going to happen at the material interface. And you got to understand what that interaction is going to be, because you want to ensure there is going to be a long-term reliability. If there is strain, stress, and all those things going to happen, you are going to start seeing some warping issues. You're going to see some cracking, and all those are going to result in long-term reliability failures.
Yeah. So I mean, Chuck, what strategies are being employed to try and mitigate this stress in these packages?
Well, clearly one of the keys is trying to manage the thermal management itself. Because one of the challenges, especially with the way processor technology has gone, is that now inside that little tiny package, we don't have uniform temperature.
Right.
So the thermal profile is, 30 years ago we looked at, okay, how much heat were we getting out of a microprocessor? Now we're looking at how much heat are we getting out of each core in the microprocessor, and if one core is running more than the rest of them, we got a hot spot.
Yeah.
And we have to deal with that in today's world. So the thermal management is, we're transitioning from the strain and modeling and understanding what's there.
Yeah.
And now we have to look at the thermal distribution, not just how do we get the heat out, but how do we get it distributed as quickly as possible?
Well, we're going to come on to the thermal stuff in just a minute. But before we do that, maybe I'll jump back to you, Grace, and ask you, what are the primary challenges in ensuring strong mechanical and electrical interconnection when integrating a variety of different materials?
So I would say it's not just mechanical and electrical, it's optical as well, because we're moving into that space very, very quickly. So, the complexity has grown a lot. And we're also moving at higher frequency. And so I think the modeling is very important, and understanding the performance, considering all of these factors, right, and all we're trying to achieve. And of course, cross-cutting across all of those is many of those interconnect technologies create heat, and we do our best to not design heat in, but we have to live with the thermal interactions. So really, there again, an emphasis on tool development is very important, particularly because with heterogeneous integration, you're no longer dealing with very vertically integrated supply chains. You're taking chips and different components from a lot of different suppliers using different processes, right? And we actually want that flexibility to be able to grow the application space. Yeah. So again, an understanding of both the fundamental requirements and then understanding of the processes and materials that are being used, so we can accurately model them in advance of building, because these are quite expensive modules, particularly at the high end that we're building. So we want to be, I think investing in tools at the moment is really one of the key challenges as an industry, and that we have to share data to enable us to develop some of those core understandings and develop the knowledge base to support swift and effective heterogeneous integration.
I mean, would you be looking at developing other sort of bonding techniques to try and deal with this?
Sure. I mean, the industry's always looking at ways of doing that better, but it's about, can you do it in high volume, right? So again, you need, I think, the engagement all along the supply chain, right? There are lots of research level techniques that are out there that can give specific performance benefits, but are they going to be scalable?
Well, this is, before we started the panel today, this is what we were talking about, whether, the transition towards using panels for assembly, that would be the best method going forward. But that's going to require a huge change in tooling within the industry.
The EDA tooling, upgrading the EDA tools is of significant importance. And coming back to what Grace mentioned, like it's also like when we are talking about heterogeneous integration, like it's not only vertical, but it's also x-axis, and so in z-axis we start seeing more and more 3D stacking, and there are different bonding interconnections, like you have solder bumps, you have micro bumps, you have thermal compression bonding, you have hybrid bonding. All of this are happening onto the same package.
Yes.
And now you have silicon chips, you have silicon interposers, you have sensors, and all of them are using different bonding techniques. So when you are putting together all this bonding interconnection materials onto a single package, there is a lot of precautions that needs to be taken. If not, all this package, all these components are kind of interconnected into a single package, and this package needs to perform electrically, mechanically, functionally. It needs to perform. So any thing that goes wrong or in the bonding techniques or the interconnections, it's going to cause a complete failure. Now, the good thing about this package is, since it's a heterogeneous integration, it becomes easier. If something is not right, you could just take that package out, chip out, replace it. But again, it's a lot of challenges, and that's where the EDA tools and how it's been upgraded to meet today's demands and even future demands, it's going to be critical.
Right. Okay. I mean, one of the other big things, of course, is it really comes down, as we mentioned earlier, the thermal management. In terms of these heterogeneous materials, the heat dissipation, and so what sort of emerging methods are coming out to improve the thermal management side of these packages?
I apologize. I was anticipating connections.
You're anticipating what? Sorry,
interconnections. As opposed
no.
I think that really probably the most, and it sounds a little maybe a little strange, but I think probably the most important thing that's coming out in terms of thermal management is that we now have much more modeling capability on thermal management.
Right.
Because we can't change the physical properties of the materials, and we can't really change the methods of assembly dramatically, because it's everybody always loves new technology, but the reality is that technical risk is the highest risk in any product in the market.
Yeah.
And if you've got a dominant market position, you're not going to risk that position just to try out a new technology, because
it's true. I mean, a lot of engineers are very resistant to change. They
right.
If it's working, don't break it.
Yeah. Everybody thinks that that a brand new technology that cuts your cost by by 50% in a particular area, it has to be adopted. But if the risk is too high, it's not going to happen. So I think that in terms of thermal management, it's our ability to model it better. And then what we're going to be able to do, this is again a tangential impact, is the people who are designing the software and laying out the chips are going to have to arrange the chips in a different manner in these structures. And the software is going to have to be designed so that it distributes the heat properly. And that sounds funny maybe, but it really is necessary that if you have an 8-core processor, you need to be balancing the workload on those 8-core processors. You can't be running the 3 at one end of the chip all the time.
Yeah, yeah.
And heating things up. So I think that those are some of the things that are really going to be the most important, because what we have the ability to control at the manufacturing level and the hardware level is much smaller. All we can do is try to distribute it more. I will say I do believe that particularly for large applications, like for the new machine learning centers where we're putting in a lot of, and we've got server farms and things like that. In those areas, you're going to see even more use of liquid cooling, as opposed to air cooling. What we carry around in our pockets and what we put on our desktops is we might have some thermal mechanical cooling systems in there to get the heat from the core out to where the air cools it. But we're going to be stuck with air cooling there. But in the big server farms and the supercomputers that are doing weather modeling, we're going to use liquid cooling.
Grace, there's a lot of work being done on nanomaterials, which are getting put into existing compounds, etc., that can change or alter these characteristics, that can improve. At the moment, they're doing ESD capability, but there are other ones that they're looking at to increase the thermal capacity of the material or the strength of the material.
Absolutely. And apart from the modeling, simulation, software, there is also significant improvements in the thermal materials, interface materials, the things. So you have novel thermal grease, you have like phase change materials. So there are so many new technologies that's been developed. Another thing that also a lot of focus is also been put into is redesigning the package architecture, wherein now you are putting heat sinks or even putting some cooling systems or having ability to cool this chips as the heat is getting dissipated. So it's all about how you can balance and improve and reduce the impacts and not have like significant hotspots on the package.
Okay. So let's move on. Lots of areas I'm trying to cover here in the short space of time, but let's talk about the problems with signal integrity and maintaining or minimizing parasitic effects in these packages. Who wants to go first? Let's start with you on that one.
Yeah, sure. Well, it's always, and I think, just on the last question, you have to think of it from a system solution perspective, right? Yes. And that's always, so we actually have more technologies available for us to pick from, which is wonderful if you're packaging nerds like us. But it does make it much more complex, right? But it does mean you can tweak. So, you can tweak for thermal performance, but you cannot at any cost reduce the fundamental electrical performance of these modules. So again, a very good characterization of the electrical properties of the materials in their base state, but also how they interact when they put into these different packaging architectures, right? So, we talked about liquid cooling, and, the data center guys are looking at this as a great way of reducing thermal dissipation and increasing their efficiency. But everything that we are shipping right now in data centers has not been designed to be immersed in any variety of different oils and chemistries for X amount of years, right? So we're having to go back to the drawing board and do fundamental characterization of what happens to our materials in these different environments, right? And so I think it will take some time. The industry is very aware of it and is already starting to address it at both the kind of individual, at the interconnect level, all the way through to the system, a final system level.
Absolutely. And just because this was something interesting that I recently came across as I was communicating with few customers in the data service, there is a lot of focus been put on the component level, but there is also on the systems level, as Grace mentioned, because when you have, say, for example, a printed circuit board that has all these chips, like you have a circuit board with flexible sleeves, flexible components, all of them, once it gets into a dielectric fluid, in a cooling system, you are going to you need to ensure that there is no contamination, nothing has been left behind on the board surface.
Yes.
Because even if the board is perfectly clean, there is no issue, there are no fluxes, residues. There are plastic materials, there are silicon materials, and all those, if there is even a likelihood of some leaching that could happen, that is going to disturb the dielectric values, I would
Values,
say,
yeah.
for the liquor immersion cooling fluid, and that could have a significant impact from the heat
Right, yeah.
standpoint. So that's going to reduce the lifespan of that system itself.
Yes.
So that is another thing as we are communicating with the data servers, and it is something that they are aware of, and that's where a lot of testing has been happening at the systems
Right.
level.
Yeah, you're absolutely right. So let me go back to my original question, which was basically we were talking about the integrity of the signal integrity and minimizing the parasitic effects of these packages. Do you have any comments on that, Chuck?
Well, I mean, because we're changing the material stack so dramatically and using so many various materials, we are definitely running into challenges in terms of how we manage signal integrity. But for example, we're in a frequency level now where even with digital circuits, and we have been really for a couple of decades, where we're not really operating in a digital world anymore. Digital clock rates are so high and processing rates are so high that we're actually operating in an RF world already, and have been for long enough that the designers understand that. The thing that's changing with this is we're putting a lot of those signals closer together,
Right.
and we're learning things that, like, for example, you're trying to make the signal path the same length. Well, when you're operating at a few megabits per second, a meander line was a perfectly satisfactory way of matching signal transmission length. Doesn't work when you get to RF frequencies because there's too much crosstalk.
Yes.
We used perforated ground planes for many years to increase the reliability of multi-layer structures. Can't do that anymore because every hole in the ground plane is a discontinuity to that signal going across the top of it. It sees that gap in the ground plane. Well, we're getting to the point where we have to put ground lines on each side of a signal line so that we're actually creating a coax line on the circuit. So our requirements for circuit density are increasing because of the speed that we're putting in place.
Yep.
And one last comment about that from a material standpoint is that we're going to the point where our materials are getting to layer thicknesses where we're no longer dealing with bulk material properties. We're now dealing with nanomaterial properties.
Right.
We're dealing with very highly activated surfaces. They're not exposed surfaces, but they're still very highly activated because they're so thin.
Yes.
And I see that as one of the big challenges we're going to see with hybrid bonding. People aren't seeing it yet because our geometries are still way too large to see them, but we will see those.
It's going to come.
So, in summary, the whole heterogeneous systems of materials are going to make the design more sensitive.
Yes.
And we probably are going to see a lot of failures before we really figure it out, because we can model it till we die, and we won't see everything because of the complexity of the system now.
Right.
In a few years, in another decade, we probably will have all those tools in place. But we still have so much to learn about how, when you have 4 different materials interacting with your signal line, what is that impact really going to be? We don't know that yet.
Yeah. Yeah.
It does need a lot more focus on the design rule changes that needs to be focused on at the board level, at the package level.
Well, I was going to say there's a lot of talk of bringing the heterogeneous compatibility out to the board level and making the whole assembly more compatible. So I think that'll go some way towards helping the situation.
That's absolutely true. Like at the board level, there has to be and that's why there is a lot more focus on high density interconnect because the typical FR4 boards cannot meet those challenges.
Yep.
And so the spacings, copper conductor spacings, and all those has to be so critical when it comes to this type of heterogeneous integration packages that, and again, the industry is learning because all these things, there is all a demand for it.
Yep.
And there is a technology is moving at a much faster pace, like hybrid bonding. Again, it's been in the industry for more than 30 years. It's not new.
Yep.
But now there has been renewed focus because there is a need for it.
Yes.
But now the need is there, but how do we get to that? And with all these things and with signal integrity, high frequency, again, you need to ensure there is no specks, no particles, no metallic particles, non-metallic like
Yep.
fibers. So technical cleanliness becomes an important
Cleanliness is
topic.
really
then.
important, yeah.
So it's all about identifying which are the critical particles that could cause a signal distortion.
Yep.
And you need to eliminate or focus on those aspects, which ensures that you get a reliable signal and you don't have any of those distortion losses.
Absolutely. Well, guys, we're afraid we're running out of time, but we've had a fantastic debate so far, and literally just touched on this subject because there's so many aspects to it as well. But we're going to be talking about it I'm sure, for years to come. So I want to thank you very much for coming in. Chuck Bauer from Technique Corporation, Ravi Parsathare from Zestron, and of course, Grace O'Malley from INEMI. Thank you all for taking part. And thank you to our audience today for watching.
The Arch FX manufacturing platform. Processing over 1 trillion data points each month. Bringing value to every level of your organization. That's manufacturing insights for tomorrow.